DATSCON presents Properties of Triangles. Recall that a triangle is a polygon with 3 sides and 3 vertices. Each one of this is called a vertex and the plural is vertices, and there are 3 sides of the triangle. A triangle is named by its vertices. So if we call this point A, this point is B, and this point is C, we say this is triangle ABC. No matter how big or small a triangle is, the 3 angles in a triangle always add up to 180 degrees. Let me write that down. The sum of the 3 angles in any triangle is always equal to 180 degrees. One way to classify triangles is by the lengths of their sides. In an equilateral triangle, all 3 sides have the same length. So we have all equal sides. All sides are equal. And all angles, all 3 angles are also equal. And I've already said that the 3 angles in a triangle add up to 180 degrees. So if all 3 are equal, then each one is going to be 60 apiece. 180 divided by 360. An equilateral triangle typically looks something like this. And we have this side the same length as this, the same length as this. And no matter how big or small the triangle is, you could have another equilateral triangle that's smaller than this. So that this side is the same length as this one, is the same length as this one. But the point is, as long as it's an equilateral triangle, this angle is going to be a 60 degrees, this angle is going to be a 60 degrees, and this angle is also going to be a 60 degrees, and the same with the smaller triangle. All 3 are 60 each. In an isosceles triangle, two sides are the same length. 2 sides are equal. When I say equal, I mean equal in length. And 2 angles are also equal. The third is not. Let me draw an isosceles triangle for you. And as you can see, this looks different from an equilateral triangle. I have made this side the same length as this side, and this side, the base, is not the same length as the other 2. You could also have an isosceles triangle like this, in which the base is the longest side. This side is the same length as this side. Further, in an isosceles triangle, the angles opposite the equal sides are equal in measure. So this angle is the same measure as this angle, and similarly this angle out here is the same measure as this angle. And that measure can be anything as long as the 3 add up to 180 degrees. And the third angle is different from these 2. If they're all equal, it becomes an equilateral triangle. 60, 60, 60. And then we have something called a scalene triangle. Let me write that name down. I think I'm going to do it here. Scalene triangle. In a scalene triangle, all 3 sides are different in length. and all three angles are different in their measure, let's say in degrees, different in measure. And typically a scalene triangle would look something like this. All three sides different in length. This is not the same as this one, and they're both different from the third side. And like I said, the three angles are also different. This is not the same as this one, and they're both different from this one. Let's talk about something called similar triangles. Similar triangles. Let's say we have two triangles, one big and the other one not as big. Let's name the first triangle as ABC and the second one as PQR. Let's also say that even though the lengths of the sides on triangle ABC are larger than the lengths of the sides on triangle PQR, the angles on triangle ABC are exactly the same measure as the three angles on triangle PQR. So we have this angle is the same measure as this one the same measure as this one, and this one the same measure as this one. That's when we say the two triangles are similar. It's as if one is a miniature version of the other, or one is an enlarged version of the other, whichever way you want to look at it. Such triangles are called similar triangles. And on similar triangles, the ratio of the corresponding sides are equal. So what I mean is, the length of AB, if you take the length of AB and divide that with the corresponding side on this triangle, not any side, the corresponding side, which is PQ, the side that has got the same two angles as the side AB on the other triangle. So the corresponding side for AB is PQ on the other triangle. So if you do AB over PQ, find this ratio, this fraction, that will be the same as the length of AC over its corresponding side, which is PR. So this is going to be AC over PR, and that is going to be equal to, you guessed it right, BC over QR. And you can actually use this property of similar triangles to find the lengths of unknown sides. Let's say, for example, this is a 5 unit and this is a 10 unit. That means if you do AB over PQ, that's 10 over 5. So that ratio is 2. Now let's say if they tell you that, okay, BC is, let's say 20. Can we find QR? Yes, we can, because we know that the ratio is 2, which means 20 over QR is going to be equal to 2, and therefore QR has to be equal to 10. There's a very important theorem related to triangles, and it's called the triangle inequality theorem. And it tells us that in any triangle, no matter what type of triangle, let's name the three vertices as A, B, C. Usually it's a convention to denote the vertices of a triangle, or for that matter any polygon, with capital letters, and then you want to name the side opposite to that vertex in the corresponding small letters. So let's say this is BC, length of BC is A. Similarly, length of AC, which is opposite angle B, is a small b, and this one's a small c. Now, the triangle inequality theorem tells us that in any triangle, the sum of the lengths of two sides will always be larger than the length of the third side. So that we have A plus B is greater than C, A plus C is greater than B, and B plus C is greater than A. Let's now look at some useful formulas. The area of a triangle is given as the product of 1/2 times its base times its height. And in a given triangle, the base and height are not fixed. You are free to choose your own base. Let's say you want to pick this one as your base. Then the height will be the perpendicular distance of the opposite vertex to this base. So that becomes your height. On the other hand, if you want to pick this as your base, then the height will have to be the perpendicular distance of this point on the base. And that height can actually lie outside the triangle, as you can see. The key point is to make this angle a 90 degrees. When we talk about the height or we talk about the distance of a line from a point, it always has to be the perpendicular distance. And obviously, as you choose a different base, the height also changes and the product B times H is always fixed, so that the area of the triangle is independent of your choice of the base. There's another useful formula you could use to find the area of a triangle, especially when you know the lengths of all the three sides. Let's have the length of this side as A, the length of this side as B, and the length of this side as C. The perimeter of the triangle obviously is equal to A plus B plus C. Now let us define something called the semi-perimeter. Semi-perimeter, you can put a hyphen if you want, doesn't really matter. The semi-perimeter is equal to, as the name implies, semi means half. So you do A plus B plus C, the perimeter divided with 2. And the area of the triangle is given by square root of, it's a big square root, S. S is what? S is the semi-perimeter, so let's call it S. Times S minus A times S minus B times S minus C. So you have 4 factors under the square root. You have the semi-perimeter minus each of the 3 sides taken separately. And if you take the square root of all of that, it gives you the area of the triangle. In a triangle, you have something called a median and a centroid. Let's talk about the median first. Imagine you have a triangle. It can be a triangle of any type. And the median is a straight line that joins a vertex to the midpoint of the opposite side. So you have a median here, and this point is the midpoint of this base of the triangle. Similarly, you can draw another median that joins this vertex with the midpoint of the opposite side, and then with this vertex with the midpoint of the opposite side. And as you can see, the medians, the 3 medians on a triangle, actually they meet at a point. This point is called the centroid. So you know median, you know centroid. Now let's say you know the coordinates, the xy coordinates of the 3 vertices on this triangle. Let's say this is x1 comma y1. This is x2 comma y2. And this is x3 comma y3 on the xy coordinate plane. Then the coordinates of the centroid is given as x1 plus x2 plus x3 divided by 3. That's the x coordinate of the centroid, comma, the y coordinate of the centroid similarly is y1 plus y2 plus y3 divided by 3. There's something called an incircle. Incircle. And that is the largest circle that can fit into a triangle, into a given triangle. I'm just going to draw the circle first. It's easier for me. And then go on to draw the three sides on the triangle. I think I'll extend this side a little more. Okay, there you go. And this indeed is the largest circle that can fit into this particular triangle. The circle just touches the three sides of the triangle, and therefore we can say the three sides are tangent to the circle. In other words, if you were to connect the center of the circle with this point, and this point, and this point, they will all be at 90 degrees to the three sides. And the radius of the incircle is given by the formula A over S, where A is the area of the triangle and S is the semi-perimeter of the triangle. Find the area of a right triangle. So this is a 90 degrees, and let's have the sides as 3, 4 and 5 units. We are actually going to find the area in two different ways. One way to find the area, of course, is 1/2 times base times height. So if I take 3 as my base, this is equal to 1/2 times 3 times the height is the perpendicular distance of the opposite vertex from this side, and therefore that's the 4 side. So this is equal to 4. This is equal to 1/2 times 3 times 4 is 6. So the area is 6 square units, or 6 units square. Now let's try and find the area using the other formula that we just learned. Area is equal to square root of S times a big square root S minus A, S minus B, S minus C, where S is equal to the semi-perimeter 5 plus 4 plus 3 all over 2, which is equal to 5 plus 4 is 9, 9 plus 3 is 12, 12 divided by 2 is 6. So we have square root of S is 6, so we have 6 times 6 minus, let's say this is A, this is B and this is C. So 6 times 6 minus 3 times 6 minus 4 times 6 minus 5. Let's simplify. Square root of 6 times 6 minus 3 is 3, 6 minus 4 is 2, and 6 minus 5 is 1. So that's square root of 6 times 3 is 18, 18 times 2 is 36, times 1 is 36. And that's 6 square units. So no matter which formula you apply, you get the same answer. The area of the triangle remains the same. Two sides on a triangle measure 7 centimeters and 10 centimeters. What could the smallest and largest length of the third side be? And this problem is a direct application of the triangle inequality theorem that tells us that the sum of any two sides on a triangle has to be larger than the third side. So if you name the third side as x and imagine that to be the smallest side, let's say x is the smallest of the three, obviously the largest side is the 10 centimeter side. And therefore we have x plus 7 is greater than 10. The sum of any two sides has to be greater than the third side. Which means if you take the 7 on the other side, that is subtract 7 from both sides, you have x is greater than 3 centimeter, let's say, put down the unit. Even if the smallest side were to be 3 centimeters, the two would add up to 3 plus 7, which is exactly equal to the longest side. So even that won't work. That won't give you a proper triangle. So the smallest side has to be larger than 3. Similarly, now if you assume that this x is the largest side, which means 7 and 10 now become the two smaller sides. So we have x, the largest side, is less than the sum of the two smaller sides, which is 7 plus 10. Or x is less than 17 centimeters. So if you combine this with this, we have x is greater than 3 centimeters but is less than 17 centimeters.